The following video will review a bit of what we did last week and then give us an introduction to arrays and processing, which is the first new thing we will learn this semester. Whenever you come across a purple turn in message, pause the presentation and try to do what's asked. When you finish the presentation, you can turn in all the answers to any questions in a document and any code in the .pde file. The .pde file can be found in the Sketch folder if you go to the Sketch menu when you are in processing. I'll show you how to do that in a little bit. When we declare variables, what we're actually specifying is a name, which will refer to some memory address, and accompanying space or size in memory. If we look inside this variable's memory, we'll find ones and zeros that give us a value of that variable. So in this case, we have an integer, and the integer has a memory address of 0x45. We're going to start looking at memory addresses this way. But remember that in Python tutor, the memory address is shown as an ID. That's fine too. We have a size in memory that's a box that tells us how many ones and zeros we can have. So in this case, it's an integer in Java. It's 4 bytes, which means it's 32 bits, which means if we look at that memory location, we will see 32 ones and zeros that, if we converted it to decimal format, would evaluate to 15. And finally, we have this idea of how bits are interpreted. And in the integer version of this, those bits will be interpreted as a signed whole number. Sign meaning plus or minus, whole number meaning no decimals. Similarly, we can look at the double version of this, right? Double y equals 25.2, and it will have a memory address, and it will have a slightly bigger box that is 64 ones and zeros, which is 8 bytes, and it will be a signed decimal number. When we did this in Python tutor, we saw that we had main memory with 2 variables and the values of those variables. We should take a second to talk about what it means to interpret memory in different ways. Let's say I have 32 bits of ones and zeros, and they're all 0 except for the last 4 bits, which are 1010. We have previously seen that this bit pattern is the number 10 if we interpret it as an integer. However, if we have a float with the same exact bit pattern in memory, remember that floats in Java are also 32 bits, we would have a completely different number, because floats represent decimals, and so part of these bits will represent what's before the decimal sign, part of these bits will represent what's after the decimal sign. It's a whole process called IEEE floating point format that we won't go into, but the same bit pattern will be interpreted as 1.4 times 10 to the negative 44. So when we declare a variable, we're not just declaring the size of the variable, we're also declaring how those bits will be interpreted. In one case, the same bit pattern is interpreted as the number 10. In another case, the same bit pattern is interpreted as the number 1.4 times 10 to the negative 44. Now, if you can, pause the video and try to answer the following question. This is part of what you will turn in for this assignment. Specifically, I want you to answer, how much memory would a program with 5 doubles, 2 floats, 3 ints, 1 boolean, and 1 char take up in bytes in a Java program? You might have to look up what a boolean is, the size of a boolean and the size of a character in a Java program. It shouldn't be too hard if you don't remember from last semester. When you're finished completing this task, unpause and we'll continue on. Now let's review variables updating in memory, and we're going to do this in processing. In fact, this whole video is going to be in processing. So let's say we have a ball in processing created by the circle command with an x position and a y position and a diameter. The code of this might look as follows, with the declaration of the x position, y position, and diameter in global scope. So what I mean by that is we define them at the very top of our processing program, and that means those variables exist everywhere in our processing program, including setup and draw. If we declared them in setup, they would only be used in setup, and if we declared them in draw, they could only be scoped to draw. So this allows us to scope them to both of those and have their values be persistent through both of those functions. So what we have here is we have a size of the screen 250 by 300, or I'm sorry, 300 by 250, right? Because the height goes first and then the width. When we say height, we usually say height by width. Our x position is set to width over 2. Okay, width is actually a special processing variable that gets populated when we make the size command. Okay, so we say size, and width gets the value of 250 in this case, and height will get the value of the height of the screen, which is 300. So feel free to use width and height whenever you want, and that allows you to be able to change the screen size, and as long as you have everything in terms of width and height, your program won't appreciably change. We have a diameter of 20, so we're just going to assume a diameter of 20 pixels for right now. Okay, so what we're doing right now is we're setting x position and y position to the center of the screen, and the diameter of the circle to be 20. And if we look at draw, which runs 60 times a second, we're drawing the same circle over and over and over and over again. So we have our screen, and we should have the circle somewhere in the middle, and that's what's happening. Now remember, variable updating is where we say make the new value of my variable the current value of my variable plus or minus something or multiplied or divided by something. The way we can evaluate this is we can look at the equal sign and evaluate what's on the right hand side first, and then use that value to set the left hand side. So for example, in our x position situation, the first time draw is called, if we say x position equals x position plus 1, we have x position as 125, and similarly we might have y position as 150. This is just from the previous slide where we put this thing in the center. And the next time draw is called, the x position will be 126 and the y position will be 151, because we will take 125, we'll add 1 to it, so it's 126, and that'll be what x position will be overwritten as. It's the same thing as saying x position equals 126 in this case. And then the third time it's called, the x position will jump to 127. And y position will do something similar, go from 150 to 151 to 152. And we can continue this, and the ball will hopefully continue increasing in x position and y position. So I want you to turn something in. I want you to specifically think about what happens in the following code if I write my two update rules under the circle command. Pause the video and answer the following question. If we put the two update rules for x position and y position in the draw function after the circle command and hit play, what would the resulting pixel values be after 2 seconds? Can you draw what the circle will look like on the following image? One thing I did not include in the draw function for this is I didn't include a call to background. So you'll see a bunch of trails right now if you actually do the update rules and run it. If you want to actually not see every circle that's drawn 60 times a second, what you should do is you should make a call to background as the first line of draw and just put a number in there. 0 meaning if you want the background to be black, and 255 if you want the background to be white, and any number in between there for some variety of gray. Pause the video and try to answer this question, and I'll meet you on the next slide. Now, I want you to write some processing code to show 4 balls moving 4 directions off the screen and 8 balls moving 8 directions off the screen. So I'll show you the 4 ball version real quickly. And there's the 4 ball version. Okay, pretty straightforward, right? And I also want you to do the 8 ball version, which is down here in directional movement. All right, so it would be 8 balls, each going a separate direction, okay? Just like the 8 movement characters in old Nintendo games or something like that, all right? So you have to think about how the X position and Y position will be updated for each ball. So now I want you to notice that if we make the X velocity and the Y velocity a variable, we haven't changed much of anything, and we're still going to be moving them in one direction. All right, so I could now say X position equals X position plus X velocity. And that's no different than saying X position equals X position plus 1 in this case, because my X velocity is equal to 1. We can do this for all our variables. So in our Y position, we can say Y position equals Y position plus Y vel, which is Y velocity, if we create a Y velocity variable. And in that way, we can now have a X velocity and Y velocity be a variable, and we can update X velocity and Y velocity based on the previous value of X velocity and Y velocity, rather than just hard coding them in as 1. For example, if I wanted my X velocity to be faster, instead of moving 1 pixel to the right every time draw is called, I could say, I want X velocity to be 5 and move 5 pixels to the right. Or I want Y velocity to be 5 so I can jump 5 pixels down at a time. All right. Also notice that if we have a positive X velocity, we'll move to the right. And if we have a negative X velocity, we'll move to the left. Similarly, if we have a positive Y velocity, we'll move down. And if we have a negative Y velocity, we'll move up. Okay. This should make sense based on your 4 balls moving in the last exercise and your 8 balls moving in the last exercise. Which brings us to, what if we wanted to allow the balls to bounce off the walls? All right. We would have to take care of 4 situations, okay? And the 4 situations would look as follows. So 2 of the situations would be when X flips sign, right? And the X velocity will flip sign when you hit the right wall or the left wall. And that makes sense if you've ever thrown a ball against the wall. Where the wall is, that will be the direction that it flips the sign on, right? So if you throw the ball down, it'll bounce up. If you throw the ball against the wall, it'll bounce right back towards you. Okay. And similarly, the Y velocity should flip sign at the top or the bottom. Imagine throwing a ball against the ceiling or the ground. Okay. And so we have to think what conditions need to be met for the y velocity to flip sign, what conditions need to be met for the x velocity to flip sign. And we just have to do a tiny bit of math to figure it out. For example, if I wanted to check and see when the ball hit the right boundary or the right wall, I would look at the x position, which is the middle of the ball, and I would say that plus some amount that has to do with the diameter, some sort of math on the diameter, should be some sort of comparison with the width of the screen, right? And that tells me that the edge of the ball is touching the screen. Okay? To do this comparison, you shouldn't use equals equals. Some people try to use equals equals, and that's not entirely going to work. The reason being because your ball might jump multiple pixels, especially if you have the velocity set to something other than 1. And so since the x velocity might be jumping multiple pixels, there's a good chance it's not going to exactly equal something. So you want to look at comparisons like greater or equal to, or greater than, or less than or equal to, or less than, to figure out when it's time for the x velocity to flip the sign. Okay? There's actually two cases where the x velocity flips the sign. So one case or the other case, you should flip the sign of the x velocity. So I have some code here for you to actually implement this. And what I'm asking is, can you make a single ball bounce by completing all the to-dos in the following code? So what you can do is you can open up a processing program, you can transcribe what I've written here in code, and then look at all those to-dos in the comments and try to implement them to make the ball bounce off the walls. The first to-do in setup is to make x velocity and y velocity into a random int between 1 and 5. And I show you how to do that using this. You use the random function in processing, you cast it to an integer, and then you put in a minimum value and maximum value. I believe random includes the minimum value and does not include the maximum value. What do I mean by that? So if I say 1 and 5, I can get values that are 1, 2, 3, and 4, not including 5, okay? And I'm casting it to an int, so it can be any of those velocities is what I could set the x velocity and y velocity to. Then in draw, we have another to-do, which is update the ball position in x and y based on the ball velocity. If you look back at a few slides ago, you can see that what we want to do is we want to make the new position, or my new x position, equal to my current x position plus my current x velocity. Something like that, right? And then to-do 3 is check if the ball is all the way to the left or all the way to the right. And if that's the case, flip it in x. And then also check if the ball is all the way up or all the way down. And if that's the case, flip the ball in y. Flip the ball's y velocity. So pause the video and see if you can't figure this out. All right, so now I have another to-do to turn in, and it's making two balls bounce. As you might have imagined, so if I assume both balls' diameter are 20, so we don't have too many variables floating around here, what we're going to have is we're going to have 4 variables for ball 1, x position, y position, x velocity, and y velocity, and 4 variables for ball 2, x position, y position, x velocity, and y velocity. And if we're able to implement draw correctly, we can get some sort of 2 balls bouncing around, all right? So you have to look at the draw function and update it to have 2 balls bouncing around now. Press pause, try to figure that out, and I'll see you in the next slide. All right, So now, what if I came here and I said, I need you to make 10 balls bounce? How many variables would you need? Well, we can kind of think about this and say, for 10 balls, I would need an x position for each one, a y position for each one, an x velocity for each one, or a y velocity for each one. All right, and if I add those all up, that would be 40 variables. Okay, so we would need 40 variables to keep track of 10 balls. Clearly, this isn't going to work. We need a way to represent and easily manipulate 10 variables. For example, 10 x positions at once, from x position 1 to x position 10. To do this, so if you see here, we have x position 1 to x position 10, and each one of those have values. Maybe they were just picked using the random function between two values. All right, and we have 1 to 10 there. Okay, well, to do this, we need a new data type, okay? And it's called an array, and it's denoted by the open parentheses and close parentheses, okay? And what that means is that instead of asking for the memory space of one integer variable, we ask for the memory space of many integer variables at once. In this case, we are asking for the space of 10 integer variables, and that's the code to make my x position refer to 10 integer variables in memory. So what we're saying here is we're saying create a variable named my x position, have it be an array, meaning it's going to refer to multiple integer values in memory. And we know they're integer values because we have the int at the very beginning. Okay, so this is not a single int, this is many ints. And have it hold 10 integers, okay? So we say new int 10, and that means it's gonna hold 10 different integers. All right? We can think of this as my x position holding 10 boxes in memory, right? In this case, my x position would have 40 bytes in memory. Now, we have a few questions still to answer, all right? We have to figure out, how do we get to each one of these individual boxes in memory, okay? We start by using something called an index, and in Java we have something called zero indexing, meaning the first element or the first integer will be at index value 0, and that will make the last integer be at index value 9. If you think about it, if you count from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 10 numbers. So what this means is that if we have an integer array of 10 numbers, the first one can be found at index 0, and the last can be found at index 9. There's a good reason for this that we will go into when we look at the memory of an array. For now, just remember the final index is 1 minus the length of the array. So right now, the length of the array is 10. Our final index can be found at 9. And our first index can be found at 0. To get a particular integer, we merely put the number 0 through 9 inside the square braces of the array variable name. In this case, we've created an array of 10 integer values named my x position, and the first integer value can be found at my x position 0, and we set that equal to 254. The next integer value can be found at my x position 1, and we set that equal to 90. The next x position can be found at my x position 2, and we set that equal to 83. Excuse me doing a typo here. There should be a capital X, etc., etc. We put the index value in the brackets to get a particular integer box, and each index can be treated like its own integer. All right, so we had xpos before, and now this is an x position, this is an X position, this is an X position. They're each integer variables, and we can do everything that we do into an integer variable with these integer variables. For example, I can give them values, like I'm doing here, and I can print them out with system.out.println. And you can try that out if you would like. What really makes arrays powerful is that we can manipulate them using for loops. This is a big part of why we start using arrays to deal with data, such as the data of keeping track of 10 balls. For example, here I have a for loop that initializes all the elements of X position to a random number between 100 and 200. So imagine I have a screen size of, 1940 or whatever, or 800, right? I'm gonna make sure that I have the balls starting somewhere in the middle, but not specifying exactly where they are. And so they're gonna be at these variable places in X. Note that we're going to start at index 0. So I've created an index variable being the control variable for my for loop. We're going to end at index less than 10. So we're not actually getting to 10, right? Because we're saying strictly less than, which means index is going to, as it increases by 1, go from 0 to 1 to 2 all the way to 9. And then when it gets to 10, it's going to evaluate to false and kick out of this for loop. All right? Now, the most important thing here is that that index is also used here to get the index at my X position. We are going through every box of my X position. We're going from index 0 to index 1 to index 2 to index 3 all the way to index 9. And we're setting it to a random integer value, something between 100 and 200 in this case. So look at that really quickly. Look at this kind of idea that we're going to make sure the for loop goes through one time for each different integer variable in my X position. And notice that it really doesn't take that much more code to go through 10 different numbers than it would be to set one number, right? As long as we set up the for loop correctly. And that is the power of for loops with arrays. There's also something that might make life easier here, and that is the length of the array is stored in my xposition.length when the array is created. This is in Java and C++, this does not occur. So when you take that class, you will have to keep an array length variable hanging around. But in Java, what's nice is that we can just say my xposition or whatever the array name dot length, and when we create a for loop, that means we can always start at index 0 and go to the array name dot length, index less than the array name dot length, and that will always get us through every element of the array. Okay, so that's something nice that you can kind of think about and understand why that's the case. Length in this case, right, my xposition.length will be the number 10. So it'll just evaluate to the number 10. So there's no difference between the bottom and the top. But the advantage of the bottom is that later on, if we decide to make 100 balls, so we try to make my xposition, we want to do 100 balls instead of 10, well, my xposition.length will then evaluate to 100, and there's no difference in initializing 100 xpositions as there is to initializing 10 xpositions using the code at the bottom. Whereas the code at the top, you would have to change that 10 to 100. And that's why we will get in the habit of using the dot length parameter. So there's no reason we can't take our 40 variables and convert them to 4 arrays of length 10. Think about it. So now we're going to be representing 10 balls, and we've represented all the values for those 10 balls. And if we use the for loop in interesting ways, we can actually populate these things and then update these things just like we did with 1 ball and 2 ball. There really isn't that much of a difference. Let's look at some code where we can accomplish this. So I have a turn in here, and it says do the to-dos in the following code. All right, so the first to do is initialize all well, let's actually look at the 4 arrays created at the top. So there's 4 global arrays: x position, y position, x velocity, and y velocity, each holding 10 integer variables. There's a diameter of 40. You can make that whatever you want. And if you want to see keep track of a radius, go for it. Radius is just diameter over 2. Notice that I made these final so that they won't change. That just makes them constant, right? You can set them once, you can't set them again. And that's a keyword in Java. If you don't remember that, you can look it up in the book. We have our size as 1600 and 960. You can really make it whatever you want because you can use width and height so that it doesn't matter what the size is, it will always work. And then I want you to initialize all 4 arrays as follows. For each ball index, I want you to make the x position random and go from 100 to screen width minus 100. All right, so that just gives you a little bit of buffer so it's not hitting the margins of the screen and not getting stuck in the screen. Using int random min comma max. Make the y position random and go from 100 to screen height minus 100. Same kind of deal, giving you a little bit of margin from the edge. Make the x velocity be random and go from 1 to 5. You've seen how to do that before. Make the y velocity be random and go from 1 to 5. Okay, so you're going to go through each element of the array, right? So index 0, you're going to do all of this, and then when index equals 1, you're going to do all of this, and when index equals 2, you're going to do all of this, and when index equals 3, you're going to do all of this, all the way to index equal to 9. And then in our draw, which runs 60 times a second, we've got a call to background. That's just going to give us a nice dark gray to draw things on top of each time we come through. And then we have a second to do. For each ball index, update position based on velocity. Okay, so that means we're updating all the elements of my x position based on my x velocity. And we're updating all the elements of my y position based on my y velocity. And keep in mind that once you put a number inside of these brackets, you have essentially just an integer. So you can add like my x position 1 plus my x velocity 1. Okay, hopefully that makes sense. Check if the ball is touching a wall, and if so, update velocity. And you have to check, if the ball is touching a wall in x position, the right or left wall. And then you also have to check if the ball is touching a wall in y position, the top and bottom wall. And in each of those cases, you either have to flip the x velocity if it's the left or right wall, or flip the y velocity if it's the top or bottom wall. And finally, draw the ball in its new position using the circle command, right? So circle and whatever the x position of that particular ball is, whatever the y position of that particular ball is, right? And whatever diameter you have. And if you do that, you should be able to have 10 balls bouncing around your screen. Struggle with that for a bit, and once you figure that out, there's actually no real difference than making 100 balls bounce around the screen or 1,000 balls bounce around the screen. Think about that. How would you change this to make 100 balls bounce around the screen? You have to make some changes, but you really don't have to make too many. All right. What's amazing is that once we complete the 10-ball program, there's nothing to making 100 balls bounce or 1,000 balls bounce or 10,000 balls bounce. There's no difference in code length for sure. By using arrays with for loops, we can suddenly create a complex system, or more complex systems, I should say, without too much code. And that's the power of arrays, right? We can use them with for loops to create complex systems pretty quickly in a limited amount of code. Notice it's just 1 page of code or something like that. In the lectures to come, we will talk about the memory implications of arrays, but for right now, just appreciate how quickly we can keep track of an unlimited number of things that behave similarly, and how the array and for loop enable all of this by working together. That's all I have. Please turn in these assignments, get started early, and talk to me if you need any help. See you next class.